Welcome to Ask and Learn.
So in question 78, we're saying that capacitors can be used as electric charge counters. And we can consider an initially uncharged capacitor of capacitance C with its bottom plane grounded. And then a plane connected to a source of electrons. So we have a lot of electrons. Okay, if we say part A, if n electrons flow to the capacitor's top plate, shows that the resulting potential difference V across the capacitor is directly proportional to n. Okay, this is a simple one because the amount of charge, if we have n electrons flowing to the top plane, the amount of top is n times the charge of electron. And then with that, we know the potential is Q over C. So we can say it is an E times QE over C. And apparently this is proportional to n, to the amount of electrons flowing onto the top plane. Let's look at part B. Assume the voltage measuring device can accurately resolve the voltage charges of about 1 millivolts. Okay, what value of C would be necessary to detect one new collected electron? Okay, so what that means is that we have this relationship voltage and zero, and then one more electron Q is going to change by delta Q is 1.6 times 10 to the negative 19, and then we'll see such that voltage can increase by at least 1 millivolt. Okay, so that is we have delta V equals delta Q over C. In order to have that, C, to have voltage larger or equal voltage equals this or equal to 1 millivolts, we need to have C equals delta Q over delta, and it has to be smaller or equal to a certain number. And delta Q we have 0.6 times 10 to the negative 19 coulomb, and delta we have 1 volts is 10 to the negative 3 volt, and that gives us 2 times 10 to the negative 16 farad. And the capacitor has to be at this value because the smaller the capacitance, the larger the change of V. So it's actually smaller or equal to this number. Finally, we have part C. Part C says, using the modern semiconductor technology, a micron-size capacitor can be constructed with parallel conducting plates separated by insulating oxide of K equals 3, D equals 100 nanometer. Okay, so given these two numbers, what is the required value of L for as a length of the side of the square planes? Okay, so what is that saying is that we already determined that the capacitance cannot be larger than this value 2 times 10 to the negative 16 farad. And now we have to actually into the construction of a capacitor. So a capacitor has this formula: C equals L naught K times A over D. And A, because it's squared, it's L squared over D. Now we're told what we know what D is, means that what type of L will make sure C is smaller than 2 times 16 farad is in part B. So in order to do that, we can just solve this inequality. So L has to be smaller or equal to square root of 2 times 10 to the negative 16 farad times epsilon times K times D. Okay, so we can use the numbers. 2 times 10 to the negative 16 farad times 8.85 times oops, I'm sorry. These two numbers is supposed to be in the denominator. 1 over epsilon k. Okay. So in the above, we should have D, which is 100 nanometer. So that's 100 times 10 to the negative 9. In the bottom, K, which is 3. And then we have epsilon, which is 8.85 times 10 to the negative 12 farad per meter. Okay, so we take this and we find that this is to 7.76 times 10 to 7 meter. Okay, it's around 0.8 micrometer.